All right, we are going to take a look now at topic 6.6. This is our introduction to enthalpy of reactions, looking at some guided notes here. So we've gotten a little bit of this in our previous section on calorimetry. So that was topic 6.4, where we were using different methods to find the delta H of the reaction. So now we're going to look at another way we can use that value and relate it to our reaction. So there are two ways to show the energy associated with a reaction. It can be written separately as a delta H value. So we can see down here we've got an endothermic and an exothermic reaction. So if we want to show that it is written separately as a delta H value, we'll have the reaction and then next to it the delta H. Okay. Now we know it's exothermic versus endothermic based on the sign. All right, the sign is going to indicate positive endo or negative exo. So we can see here we've got a positive value that indicates we're adding energy to the reaction, so that's endothermic. A negative value indicates that we're losing energy from the reaction or producing that energy, therefore it is negative. Now, the second way that we might see this is it can be written within the reaction. So if we write it within the reaction, it's going to look a little different. My other highlighter, you guys can see. So if it's written within the reaction, we're going to indicate if it's endo or exothermic based on its location. So here we can see that the energy is written right there or right there. Notice that both sides are pluses. We never subtract in a chemical reaction. We only add. So the way we show if it's endo or exo, if it's endothermic, it's going to be a reactant. So in this case, endo is reactant. We're adding it to the reaction, adding it to the system to make the reaction work. And if it's exothermic, it's going to be a product. We're producing that. So these chemicals are reacting to produce ammonia and energy. So that energy is being given off by the reaction, it's exiting. This is going into the reaction, so endothermic. So those are two ways that we can look at the energy. If we want to do a calculation with this energy, we need to make sure we're paying attention to the sign. So if we see it as a product here, we have to keep in mind that's exothermic and it's a negative energy. It's being released from the system. Okay, that energy is the amount of moles of each chemical involved in the reaction. Excuse me, it can be used in conversions. So a lot of times we'll also see this written as kilojoules per mole reaction. And that's really how we can interpret and use this to help us convert between moles and kilojoules. So we're going to take a look at how we actually do that. So let's take a look at an example of how we might use this. So if 20 grams of hydrogen gas, so we've got hydrogen gas, we've got 20 grams of it, is used in this reaction, how much energy is produced? So we can see here, we know that if 3 moles of hydrogen is used, we will produce negative 46.19 kilojoules of energy. So we want to know, well, if we react 20 grams, what is that amount of energy? So we have to do some calculations. This is a stoichiometry problem. Okay, we're going to write the hydrogen as H2 because that's how it appears in the reaction. And we're going to set up our ratio. So the first thing we want to do is, if this is telling us moles of hydrogen to our amount of energy, those are related to each other, then I need to get to moles of hydrogen so I can use this ratio. So we want to change from grams of hydrogen to moles of hydrogen. All right. In 1 mole of hydrogen, its molar mass is 2.02 for H2. So that gets us to moles of hydrogen. Now, this is per mole of the reaction overall. So we're going to say, okay, let's go from moles of hydrogen to moles of the whole reaction. So when this reaction occurs one time, how many moles of hydrogen are we using? Well, its coefficient is 3. So that's how we interpret this. We're always going to say 1 mole reaction and then its coefficient for that chemical. And that gets rid of our moles of hydrogen. Now we're looking at the whole reaction. Well, when that reaction occurs, we can see when that reaction occurs one time, so 1 mole reaction, we are going to give off, so negative 46.19 kilojoules of energy. So we're saying, okay, we know this relationship. I know how many moles of hydrogen I'm using in the reaction, and I know that the reaction produces this much energy. So if I can get to moles of hydrogen, I can use those relationships. So we're going to do that conversion. Now we just need to do some math. Now, I've seen a lot more math mistakes happening recently. Let me explain one thing. Whatever you put into your calculator first, every number that follows is in reference to that first number. So let me put it this way. If my whole problem was just the top of this, I'd do 20 times 1 times 1, of course, times negative 46.19. So I want to multiply those two values. If my whole problem was this, I'd want to divide 20 by 2.02. So the 2.02 is being divided. If my whole problem was this, the 3 is on the bottom, so it would be divided. So when I put this in my calculator, I'm going to divide by both of these numbers. A lot of us are putting a multiply between these, but using no parentheses, and so we're getting wrong answers because your calculator only knows how to do order of operations the way you plug it in. So we've got 20 times negative 46.19. That takes care of the numerator. I'm going to divide that by 2.02. And I'm going to also divide, because everything's in reference to the first thing I typed, which was this, I'm going to divide by that 3. And we get negative 152.44. Okay, so again, our significant figures are going to come from our given amount. We have 3 sig figs here, so our answer is going to get 3. So negative 152 kilojoules. Our moles reaction cancel. So the amount of energy produced from this, if I react 20 grams of hydrogen, I'm going to make 152 kilojoules of energy. And we can tell it's going to be released because it's negative. All right, so we're using stoichiometry. We've done all of this stuff before. Now we're just relating it to energy. We have another tool in our toolbox. Excuse me. All right, let's check out another one. So if 550 kilojoules of energy is absorbed by the reaction, how many grams of water will also be used in the reaction? Okay, so we want to know, hey, I'm absorbing this much energy, so how much water is that actually going to react? So we're going to start with our given amount. We're not used to having kilojoules as a given amount, but that's okay. It's a new experience. So we can see here that 241.82 kilojoules is involved in the reaction. I put those on the bottom so my units cancel out. So that much is used every one time the reaction occurs. So for every 1 mole of the reaction. So this happens once, I'm going to use 241.82 kilojoules of energy. That gets rid of my kilojoules. Now, we want to get to water, so I want to go from, okay, when my reaction happens one time, how many moles of water are involved? Well, we can get that from its coefficient. 2 moles of water. And again, we can cancel our units. Now, it's asking me to find grams, so we're going to take this one more step and change from moles of water to grams of water. In 1 mole of water, there are, 16 plus 2.02, 18.02 grams of water. We're at the unit we want, so we stop adding railroads. Excuse me. And we can calculate from there. So again, as I put this in, I'm going to put everything in the top, multiply, and then divide by any numbers on the bottom. 550 times 2 times 18.02 divided by 241.82. All right, our given amount has 4 sig figs, so 81.97 Next number is a 0, so 81.97 grams of water is used in the reaction. So if I use 550 kilojoules of energy, it will react 81.97 grams of water. So that's a pretty handy thing to be able to do, is to convert between amounts of chemical and the amount of energy we are using or forming. All right, we've got one more example to look at. So let's take a glance at this. So it says if the change in energy during the reaction is negative 975, this should say kilojoules, and I don't know what that's about. Sorry, weird typo. How many grams of NH3 will be formed in the reaction? So we know how much energy we're using, or producing in this case, and we want to know how much NH3, how much product we're also going to produce. So we're going to start with our given amount, negative 975.0 kilojoules of energy. Now, something to pay attention to, this is a negative. That's telling me that our change in energy is negative. That means our reaction is giving off the energy. It's negative. Now, my final answer is in grams. I cannot have negative grams. That is not something that exists. Okay? So that means that I'm going to have to get rid of this negative. So that's a clue to help me. When I look at this, I see 46.19 kilojoules. Well, that's a positive value in this reaction, but it's a product. It's on the product side, which tells us it's exothermic, which tells us it's a negative value. So I'm giving off 46.19 kilojoules of energy every one time my reaction occurs. So those two negatives will, when we divide them, will cancel, and we will get a positive value for a final answer. Everything else we put in should be positive. So when that reaction occurs once, how much NH3 are we using or making? We're making 2 moles of it. Now my question asks for grams, so I'm going to change from moles of NH3 to grams of NH3. In 1 mole, our molar mass, we've got 14.01 plus 3 hydrogen, so 3.03, 17.04 grams of NH3. So our moles reaction cancel, our moles of NH3 cancel, we're left with grams of NH3. So again, multiply everything on the top, divide by any numbers on the bottom. Negative 975 times 2 times 17.04 divided by negative 46.19. Okay. We get 4 significant figures from our given value. So 719 point, the 3 will round to 4 for our 4th digit. And that is grams of NH3. So that is how we're going to approach these. They are stoichiometry problems. Now, in your practice, I added a little bit of scaffolding. So I added a little bit of kind of pre-questions to help you think through what's going on, to help in your thought process. So is heat a reactant or a product? Making you guys recognize where it's located. And does that mean it's endo or exothermic? Okay, again, making you think about, is it positive or negative? Now, we can get things in grams like we've seen in our examples. This one gives us liters of oxygen at STP. That, remember, is when we can use the fact that 22.4 liters equals 1 mole of gas at STP. So we can use that to convert between liters and moles, just like we use molar mass. It's in place of that. So when it's talking about liters, we wouldn't need grams on that one. But you can only use this if it says at STP. There is one of your questions, which I have done mine. I believe it's on the next page. But it gives you information about a gas that's not at STP. When it's not at STP, that's when we use PV equals nRT. This is a good review of that. If you get stuck on that one, please let me know, and we'll do a little refresher on it. Okay, this is your gas laws. So try these out. Let me know where we have some issues, and I will help you guys out. Thanks.